Okay, welcome. We are going to analyze the motion of an object falling in what we call free fall, ignoring all frictional forces, wind resistance, and allowing it just to fall under the influence of gravity alone. This is a constant acceleration problem called free fall problem. You'll see these in physics all the time. And if you imagine this, this figure on the left side of the board here drops the ball from rest initially at the top, and the ball falls down this great distance for 4 seconds. And initially, at time 0, it's at rest at 0 velocity, but 1 second later, it falls 5 meters. 2 seconds later, it falls 20 meters, gaining more and more distance each second. 3 seconds later, it falls 45 meters, and as it's accelerating, 4 seconds later, it falls a total of 80 meters. We'll say this cliff here is 80 meters high. And as it's falling, the ball is equipped with a speedometer that can measure its instantaneous velocity. And so initially, time 0, if you look at the bottom graph, this is the data of its velocity. Time 0, 0 velocity. 1 second later, it speeds up to 10 meters per second. 2 seconds later, 20 meters per second. 3 seconds later, 30 meters per second. 4 seconds later, 40 meters per second. Increasing its velocity at the same rate each second, so it's increasing by 10 meters per second each second. Now, the accepted value for the acceleration due to Earth's gravity is closer to 9.8, but we're going to use 10 as the acceleration constant for free fall, just to keep the math simple. Now, if you look at this graph, what would the graphs of its position or distance versus time look like in this graph of velocity time, and how can you analyze the slopes of those graphs? So start with the distance time graph. At 0 time, 0 distance, 1 second later it falls 5 meters. So you'll have this little line segment. 2 seconds later, it's fallen to a total of 20 meters. You notice the slope's not the same, it's gotten steeper. 3 seconds later, it's fallen 40 meters. Again, it's getting steeper. 4 seconds later, it's now fallen 80 meters. And if you analyze the slopes of each of these lines, you'll see an interesting pattern. That for every 1 second of run is a different rise. If you remember, slope is always a measure of how much change there is in the y variable, or rise, per unit change in the x variable, or run. You'll see that the slopes increase. So you do not have a constant slope. You have an increasing slope. And since slope of this graph measures the change in your distance per unit change in time, which is really measuring your velocity, how your velocity changes over time, this implies that your velocity is increasing. You can see an increasing slope. Slope means velocity. Therefore, you can conclude that the velocity of the ball is increasing, hence acceleration. All of that can be derived from the graph. You can look at it more quantitatively to find the exact average velocity for each second interval if you would like, but we're going to skip that. You can try that on your own. You look at those 4 seconds, but what we want to do is now imagine if we know the exact instantaneous velocity of each second in time. So if the ball is falling, it starts at 0 speed initially, and then after a second it's 10 meters per second, to 20, to 30, and finally to 40 meters per second. Now this trend looks and appears to be linear, and it is. All these points are collinear. And if you analyze the slope between any 2 points, you will be guaranteed a rise of 10 or a run of 1. A rise of 10 or a run of 1. And that's true for all points on this line. So you have what we call linear trend with a constant slope. And if you calculate the change in the y variable, change in velocity per unit change in time, which is your slope, you are actually measuring the acceleration. And in this case, the acceleration, or or slope measures 10 meters per second each second. And that's a constant rate every second of time. Anytime you have a constant rate of acceleration, you should be able to graphically show that the data trend is linear, and the slope of that line is a measure of its acceleration rate, whereas the trend of its displacement versus time graph is not linear. It has an increasing slope. It looks to be more parabolic, a quadratic relationship. Because it's not linear, you have this curved trend.